Good afternoon, everyone. Today I want to talk about in-situ characterization of fundamentals and nanoscale dynamics that can be lead to the materials development. My name is Akihiro Kushima. I'm assistant professor in material science and engineering department. And so before I go on, let me just briefly introduce myself. So I got my PhD in Kyoto University back in 2007. Then I did a couple of postdocs at MIT and UPenn, and later I joined MIT back as a research scientist and came to UCF starting in 2017. So I started out my research career as a purely theorist. So I did atomistic simulation and also the quantum mechanics simulations like Dept. And later I tried to go beyond the time scale of current MD and do the accelerated molecular dynamics, so you can do a long time scale dynamics. And apply this method to measure mechanical properties and gas transitions, and also application for the solid oxide fuel cells. Then later I switched my research areas to in-situ transmission electron microscope. Then started studying the electrochemistry such as lithium-ion batteries, and you can look at reaction process in situ in the real time inside transmission electron microscope, and also apply this method to study nanoscale mechanics. So my research area is in the in-situ transmission electron microscopy. So I want to develop different techniques so you can see various processes in the real time in nanoscale. And particular interest at this point is energy storage materials. So I want to use these techniques to observe the reaction mechanism so you can understand what is happening in the when you do the charge and discharge on the batteries. So that you can give a feedback to the for the device development. So for the teaching, I've been teaching transmission electron microscopy and scanning electron microscopy, basically the electron microscopy course. So you can give students the fundamental ideas or fundamental theory of these devices and equipment, and have some hands-on experience so students can get to learn how to operate this equipment. And also taught design and selection materials, and some one module in the material processing laboratories. Okay. So the motivation of my research is to understand material property from atomic scale and use this fundamental information to you can contribute to device development. So to do this, I use two approaches because of my two experience in the experiment and atomistic simulations. So I want to use in-situ experiment, particularly the transmission electron microscope, to observe the dynamic process in real time and understand what is happening in a very fine scale. And use also the atomistic simulation so you can provide theoretical understanding and support to what you observed in the experiment. And you can also use atomistic simulation to predict the new phenomena or some new mechanics which was not seen before. And you can use in-situ experiment to confirm these new phenomena that was predicted by the simulation. So you can see the mutual interaction between these two methods, and you can combine those two techniques to understand very fundamental science of this material properties, and that will lead to contribution of device development. So I want to explain take a few examples on what I'm currently working on. So I'm particularly interested in the energy storage materials in the lithium-ion batteries. So recently there are lots of development in the lithium-ion batteries. So you want to increase the capacity and the more power and make it very rechargeable batteries. But as the battery contain more and more energy, there are a high risk of the explosion or the fire when they are not properly operated, or they get the cells get damaged. And there are lots of fire-related fire or explosion issues reported from the U.S. airlines, and you can see there's a rapid increase after 2000 around 2000, now you have like over 50 incidents per year for this fire-related accident. And why this lithium-ion battery catch fire? Because you want to increase the energy density, so you want to minimize all these unnecessary part that is not going to contribute to the capacities. So, for example, you want to use this the separator as thin as possible. So what's going to happen is if you have very thin separator and you do the charge and discharge, and if you accidentally overcharge or discharge, this dendritic growth of the lithium can penetrate through this separator and make a short circuit. Or if you have external damage, you can easily penetrate through this separator, and you can also cause a short circuit. And this short circuit can cause a high current that can lead to a very high heat. And also because this heat can cause the emission of oxygen from this cathode transition metal oxide. So you have in the lithium-ion battery the heat and flammable electrolyte as a fuel, and oxygen coming out from the electrolyte that can you can easily expect to have a combustion or the explosion. So there are lots of fire-related concerns in the current lithium-ion batteries. But so we are now trying to consider like all solid-state system, which eliminate flammable liquid electrolyte, and it also has very high modulus that can prevent dendritic penetrations, and that is believed to be very safe, and you can also achieve very high current, high energy densities. But even though you think it's not going to have, you're not going to have dendritic penetration, there have been reports saying that dendrite can actually penetrate through this stiff solid electrolyte. So we want to understand why this is happening. What is the method you can prevent these techniques. So here you can look at interaction at the interface in a very fine scale, because there will be lots of complicated electrochemical mechanics in a nanoscale that can lead to this fracture of this solid electrolyte, and also the penetration of this lithium metals through these grain boundaries of this solid electrolyte. And you may also see some phase changes when you have an interface between this solid electrolyte and very reactive lithium metals. So you want my near-term goal is to understand the fundamental mechanics of this complex electrochemical mechanics phenomena in a nanoscale. And this was awarded for NSF Career Award in this year. Okay, so in this technique, I've developed this in-situ technique that can directly observe reaction mechanism under electrochemical biasing. And you can also measure the mechanical force which is applied to this dendrite by combining AFM cantilever and this in-situ TM holder that can manipulate this metal probes, so you can contact this conductive AFM cantilever on this lithium metal. Then once you apply the bias, you will see this dendrite growth, and you can measure the displacement of the cantilever, and that can measure the mechanical loading applied to the dendrite. So you can see in this graph, you can clearly see the growth of the lithium dendrite, and you can associate those as with the mechanical force that has been applied to the dendrite tip. And you can see how the stress develops at the tip of the lithium metal, and eventually it will reach the threshold stress, and eventually the growth direction will change from vertical to the transverse direction with respect to the surface. So you can see the complex electrochemistry and mechanical property, mechanical interactions through this single experiment. So that is what I'm going to do for the near-term goal. And then I want to explain some of my capabilities of the group and some of the collaboration opportunities. So I'm interested in developing in-situ TM techniques. So we can look at the heating, mechanical experiment, and also electrochemistry. So I have been collaborating with lots of professors here at UCF and also outside UCF. So in my lab, we don't do any synthesis. So I'm open for many collaborations if you need any nanoscale characterization for your devices. So you can look at heating property and look at the stability of back contact of this tungsten metal oxide, the rear contact, and you can see after you heat up the device, there will be an intermixing zone that will create, that will destroy all these nicely layered materials. And you can also do mechanical testing to understand the properties of this 3D printed metal alloys and what's going to happen if you do the heating. And you can clearly see that as printed materials have very ductile properties, but if you do heating, then you will have a very brittle behavior. So you can compare these two behaviors from the exact same materials, and you can also combine it with a heating experiment to understand the phase transformation or the structural change and correlate those experiments with the mechanical properties. And for the electrochemistry, once you have a device, we can do the nanoscale testing to understand what is a reaction mechanism. In this case, we have a porous thin metal electrode for the aluminum ion batteries. And you can see because of this porous structure, you will see the, you will limit the overall volume expansion, and that can lead to the very high cycle lifetime. Okay. And there are some other capabilities we have. It's a liquid cell microscope. So you can look at, okay. So you can look at this reaction processes and actually see the dendrite growth in the actual liquid environment. It's been very difficult to do this kind of liquid cell liquid experiment because inside the TM, it's a highly vacuum. So if you put any liquid inside, the liquid will evaporate and you can no longer see the reactions. But with this very thin liquid confining cell, you can trap all this liquid and observe this actual electrochemistry happening in the liquid. And you can see this dendrite growth mechanism is different when you apply different over potential or current densities. And you can also apply this to look at this, sorry, my mouse disappeared. Okay, so you can also—
So you have almost done, so please.
Okay, okay, so I can wrap up. So you can see, look at very difficult, different mechanism. And also you can see the multiple physics interaction that you can measure the electrical property of a single nanowire and see how that property change as you apply the mechanical stress. So with that, I want to thank all the, my students and advisors and collaborators and sponsors, and also thank you for listening.
Thank you.